Hey, hope you guys are mostly done assignment 1. I have assignment 2. You can pick it up after class. They get easier, I think. I don't know. They start hard and get easy. Isn't that how it's supposed to go? Because I get lazy. So let me just finish up this Grassmann nonsense. In order to construct a path integral, you need Grassmann functions. This is a Grassmann number. These are your two generators we're going to use, eta and eta bar. Oh, I might have been calling them complex, or like the star, sorry, not complex, but, you know, to denote the conjugate. But now I forget what I was doing. Functions defined by the Taylor expansion. I think that's straightforward. Let's just talk about the calculus a bit. Because it's fun. And you sort of need it. So differentiation first. Basically what you want is a definition of a derivative that makes sense. So if you take a derivative of a Grassmann variable with respect to itself, you get unity, and, you know, if you have a, say, scalar or unity, that gives you 0. And so the definition is basically the partial derivative of a Grassmann generator with respect to, the generator for any other particle. Just gives you the delta function. And the weird thing about Grassmann differentiation is that it has to be consistent with the anti-commutator. Which means that if you take the derivative of the conjugate variable multiplied with a non-conjugate, which I don't know what you call, and you commute these two variables, these two generators, then you get a minus sign out front. That moves your differentiation operator next to the appropriate eta, which gives you 1. And so what? So you'll have minus the conjugate variable. Okay, so that's what defines Grassmann numbers, is basically that minus sign. Okay, so if you take that number that I wrote, that general Grassmann number, that's a linear combination of all the generators, of the two generators, with coefficients which are complex, remember? C0, C1, C2, C3. So let me take that number and differentiate it. So the derivative with respect to eta will just leave me with C1. And the way I've written it there, I have to commute those variables. So it's minus C3 and the conjugate. Then the derivative with respect to eta bar. Let's see, it's just C2. That'll be plus C3 eta. Just a difference in minus sign, right? So if I now take a second derivative, say of this thing here, all I get is minus C3. And if I reverse the order, like in this case, oh, sorry, this shouldn't be a bar, right? Right? Because I've gotten rid of that variable. So if I take the reverse order on here, all I get is C3. So that minus sign means that, you know, the derivative itself anti-commutes. Man, I was teaching a second-year class, and I had a bunch of these partial derivatives written out on the board, and like an hour in, some students like, why don't your 2's cancel? So just be warned, it's my dies. Worst day teaching ever. So the derivative anti-commutes. Big deal. So the fun thing is when you compare differentiation to integration. Yep.
Before you proceed, what happens with the product rule for derivative of Grassmann?
So say it again.
What happens to the product rule? Like I guess there are minus signs that you have to take care of, right?
Yeah, yeah.
It's not the usual product rule for derivative over the real numbers or whatever, right?
Yeah, I think it's. I think as long as you take account of this, everything has to obey this anti-commutator. Yeah.
Right. So basically, the recipe is that whatever variable you're differentiating with respect to, you just throw it to the left. So
Yeah, you anti-commute it to the left or right or whatever the first position where you're using it. Yeah. It gets worse. So there's no Riemann sum analogy to define integration. So integration is defined a little different for Grassmann numbers. So it's just, integration is just defined to make sense, essentially. And for example, a linear mapping or, you know, if you have a function that's an exact differential, you want that integral to be 0. So you just want sensible things like if you have a function that's a derivative. I mean, this is just for regular variables, right? Then you'll get 0 if the function goes to 0. At infinity, plus or minus infinity. So you just want sensible things like that in your definition. So to make a long story short, so the only non-vanishing integral is the integral of eta, because that's the only quantity that's not a derivative, basically. I know that's a pretty weak explanation, but so it's just natural that the integral is a non-zero quantity. Right, and same for the conjugate. And then the integral of, say, unity has to be 0. Which gives you the integrals of scalars. So this is all basically by definition. Roughly motivated by, how you want the properties of this thing to behave. So what you see, if you compare integration with differentiation up there, they're the same thing for Grassmann numbers. So we can show this actually. So let's just consider a function that we want to take the derivative or the integral of. Which is a function of the generator eta. So I'll call it F0 and F1 for my constants. Okay, so it's like A, the number, but I made it only a function of one of the generators. So then the derivative, let's see, with respect to eta, is just F1, just like the, so that's the integral, so that's just like the derivative. Which should be the partial eta F eta, which I did over there in the language of A. There's no other way to write it. It's like Grassmann numbers are way simpler than normal numbers. There's like very few things you can do with them. And the calculus is very simple because of this. There's no other way to define, these symbols basically mean the same thing. So when we see them in functional integrals and stuff like that, we just got to keep in mind these properties. So in this sense, when people say fermions are easy, this is what they mean. The algebra and the calculus that occurs in the path integral is very simple. And functions are also very simple. Right? Some general function of a Grassmann number only has very few possibilities. So I can rewrite all the properties of the integral on my general number A, my Grassmann number. And just like differentiation, the order matters. Eta bar eta versus eta eta bar. Sorry, this is messy. A should be, the way I've written it is a minus C3. Okay, so. Okay, so that's it for the general structure of the algebra and the calculus. It's dumb. It's like, there's nothing to it. So we're going to just use eta to construct the coherent states And then we can write the general path integral for bosons and fermions, just keeping in mind that if we're talking about fermions, we're talking about Grassmann numbers. If we're talking about bosons, we're talking about complex numbers. Okay, so the last thing to do in order to construct the path integral is to figure out what the coherent states are. So remember, we want to have, say, a second quantized annihilation operator acting on a fermionic coherent state, which gives me back an eigenvalue associated with that operator index. That's a Grassmann number. And the state back again. And we need this in order to construct a path integral because we need the matrix element of the Hamiltonian. And that allows us to get rid of all the operators in terms of the eigenvalues of those operators. Okay, so again, the motivation's simple somehow, but I guess the devil's in the details. And one of those details is I've defined this Grassmann algebra in a real sketchy way. But we also have to remember how the algebra of the generators interfaces with the operators in quantum mechanics. And so we just, without any proof, we just need to slightly enlarge this algebra. So we need to account for combinations of, of the eigenvalues and operators. Let's see, multiplying. So the quantum mechanics that comes into play is just that these things anti-commute. Or the anti-commutator is 0 in this case. So I think that's enough. I think so. And you might have guessed this anyway, but. So just like when you introduce operators into quantum mechanics with C numbers the first time, you just have to do the same thing with Grassmann numbers, but you need to require that they anti-commute. So now the coherent state I could try to think of some way of deriving it, or I can just prove its form, which is easier because I know what it is, because I read it in a book. The coherent state can be derived from considering this expression. So I just have a annihilation operator and a form that looks like part of the coherent state for a single particle in the bosonic case, sort of. But in order to see how this function operates on the vacuum, I expand the function, the exponential out, so I should get 1 minus eta a dagger operating on the vacuum state. Okay, so I just expand the exponential. What about all these higher order terms? Why are they 0? Right. So that's what's beautiful about all these functions. These functions, when you expand them in terms of your Taylor expansion, so these are every higher order term is equal to 0, since you can't square that Grassmann number. And this thing is like the most powerful trick with Grassmann variables, the fact that you can write 0 as eta squared. And if you're wondering where this came from, again, just go back to the first thing we introduced with Grassmann numbers. It's because if they anti-commute, right? So if it's like eta times eta is equal to minus eta times eta, then they have to be 0, right? So that's it. That's your exponential. It's just this minus this. All these other terms are 0. Let me keep writing this. I have a lowering operator operating on the vacuum, which annihilates the state. I can commute these two numbers through, or anti-commute, or whatever, and I should get, let's see, is this right? Eta, AI, A dagger, I, operating on that state. Right, so now, I can write this, A dagger operating on the state. I don't know if it helps me that much. If I reverse the order of these two things here, right, then I get the fermion anticommutator, which is delta ij, but the indices are the same, so let me do that. Then I should get something like 1 minus AI dagger AI. Yeah. Right, so. Now that's in a form that's useful to me because I can just annihilate the state, right? So I just get that Grassmann variable up front. And I can write this in terms of I can rewrite this expression as eta I all times 1 minus eta I and the raising operator. And why can I do this? Same reason, just that sketchy trick. So this term's 0. You just add 0 to something, it's fine. And so then what you get out is the thing I'm looking for, which is the eigen equation. So I re-exponentiate that, because there's only 2 terms in the exponential anyway. That was a weird proof. I wasn't sure that was going to work. I'm still not sure about it, but I think it's right. I like this thing. You just throw in zeros everywhere. Just like throwing in resolutions of the identity all the time, right? You can multiply stuff by 1. You can add 0 to anything. So this is the coherent state because that's an operator. A, that's the raising operator, and this is the associated eigenvalue. So the fermionic coherent state, then that's for one particle. So it's straightforward to extend it to many particles.
So why do we bother writing it in the exponential form there if all higher terms are 0?
Well, just because you don't have to, but when you write the general coherent state path integral, we're going to keep it general for bosons and fermions.
Oh, I see.
Yeah, so then I'm just going to replace these etas with a field that's either bosonic or fermionic. You just got to remember whether or not that field's fermionic or bosonic. And the form of the path integral is the same. Yeah, so it looks the same, or looks similar to the bosonic case. Actually, so let's do that. I think we can compare the bosonic and the fermionic coherent states. So most things look analogous. you know, the form of the coherent state functionally looks the same. It's constructed to basically look the same. So most properties carry over. Note a few peculiarities with the fermions. When I write this thing operating, say backwards if you want to call it that, on the bra, you have Grassmann variables that I've written as conjugate variables. Careful about careful about the order of the operator. All right, there's a minus sign there. Just keep in mind that the Grassmann variables are not related. You know, the conjugate variables aren't related to the real variables, if you want to call them that, by some sort of complex conjugate. They're independent variables in the Grassmann algebra. All right, so. There's no so eta and its conjugate are independent. The Gaussian integral is different. That matters, especially for non-interacting systems. And you can already imagine what it looks like. You just write the Gaussian integral. You have an exponential. But that exponential only has two terms in it, because eta squared is 0. So your Gaussian integral is different. So in terms of these two generators, that's what I would call a Gaussian integral. But that exponential is just a simple 1 minus eta bar eta. So the normalization of the overlap's different. Oh yeah, you haven't seen this yet. It's on your assignment too. When you prove the overlap for the coherent states, for the bosons, there's a pi, or pi I or something in the denominator. That comes from the Gaussian integral. So in this case, it looks different, so you have to keep that in mind when you write the overlap. The completeness relation. So I'll just write it down. So the completeness relation, which I defined before for bosonic fields. Oh, those are supposed to be etas. When I write general fields, I write them as size. That's standard in the literature. And then size can either be phi's for bosons or etas for fermions. Oh yeah, but I think I can do this one. Let's see. So let me keep it. So let me say I can be phi or eta, depending on bosons or fermions. So then this is the resolution identity over Fock space, but I have to define that thing. This will depend on whether or not the fields are fermionic or bosonic. So last time it was a complex conjugate over pi. So I want to use rho here, which is -1 for fermions, right? So it's 1 plus rho over 2. Okay, so that pi has to die for fermions. Okay, so it's not quite as easy as just swapping the fields out. There's going to be a couple of these rows crop in. And actually, one of them is really important. It's related to Matsubara frequencies. When you like analytically continue spectral functions, basically, for fermions, it turns out to be very different for bosons. Maybe I'll get to that today. I'm going to write out all the general properties in terms of these fields, these general fields psi. But let me prove one more. So that's completeness. I won't prove that one. I think you're doing that on an assignment. Let's do the overlap. Yeah, you'll do completeness for bosons, so that's good enough. Let's do overlaps for fermions. Then I'll write them all. Then I'll summarize them all. Then I think between your notes and the assignments, you'll have proven them all. So if I have eta and eta prime, coherent states. So I take that coherent state there. It has an exponential. There's a sum over all i's. Let me make, I can just drop that sum out if I want, but I can write it as a product or whatever, and then I can expand out the exponential for eta, which is conjugate, and eta prime, which isn't. Okay, so I get terms that are, so this is my, this is my overlap of two coherent states. That's all, that's like, these are the exponentials here. So I have a term that's like 1 times 1. And I have a term that's like minus times minus. Let's see, I got to get the order right. Oh, I forgot an A here. There. Okay, so I have a term that's unity, then I have a term that's plus AI, eta bar, eta prime, raising operator. So that's quadratic in the fields. I also have terms that are linear in the fields, but what happens to them? Why?
Just either A or better.
Yeah, so you're like operating on a state, and so then it'll be 0 and 1, or it'll either be annihilated. So that's all the terms you basically have. And then you can commute things. What do I got to do? If I commute this operator through twice, I get 2 minus signs. I don't know. This product's useless. 1 plus. There we go. That's just eta bar, eta, and a number operator. So number operator is a root n plus 1 out front for the raising operator, right? So n is 0, so it's root 1. And then lowering has a root n, which is 1, so you just have a couple unities there, even for fermions. So nothing fancy. So you get 1 plus eta bar eta prime. Okay, so that was just a long way of showing that the overlap for fermions, for fermionic coherent states, looks exactly the same as for bosonic. I could have done that before the completeness relation, but. And that's it. You can use that. I think that's everything you sort of need to know about relating bosonic and fermionic coherent states. What did I call it? So, oh man. Yeah, okay. So this is just re-exponentiated. Like that. I don't know. Same as bosons. Okay, let's summarize all these into basic properties. And I'll use this field, which can be bosonic or fermionic. So the definition of a coherent state, which we've shown for both. Right, so it's minus here. So it's e to the rho field and a dagger. So the eigenvalues are elements of C. They're C numbers for bosons, fermions. Rho is -1. The fields are the eigenvalues. I don't know what I called this algebra. A, the Grassmann algebra. Okay, so that's all you have to remember is that definition. I write that definition down with rho. You can apply, let's apply operators. So the raising operator, or the lowering operator. By definition gives you the eigenequation. And some of these things you've seen, just in a different sort of language. So remember that bar now is complex conjugate for bosons, and it's just the conjugate operator for fermions. So we apply a dagger. There's a minus sign you have to worry about. operating backwards, you get what you want. The overlaps of the same form. No minus sign in front, so you don't have to worry about that row. Just the thing I wrote before, oops, plus. And completeness is that thing right there. And I have all my rows in there, right? Good. Basically all you need, I think. Any questions on the coherent states? We'll use them to construct the path integral now. So remember, the reason we're doing all this is because we expect Hamiltonians in second quantized form. So you dealt with I guess that type of second quantized operator in assignment 1. In assignment 2, I'll give you a question on the Hubbard model, which is a second quantized fermionic model, C dagger C with spin. So that in that case, you know, in a Hubbard model, they just often call these A's C's, but they're just second quantized operators for fermions. And so imagine we get a Hamiltonian in this form. The goal is to write the path integral. Just to remind you of what we're doing. It could be something as simple as a non-interacting Hamiltonian. And, I'm trying to think of a simple harmonic oscillator, maybe. Why not? You could have it in K space, it doesn't matter. You can have something more complicated that's interacting, like you'll see on your assignments, which could be, say, on a lattice. So if I and j are, say you're on a lattice or you have some sort of site index, if you have a dagger A, and I and j are different indices, that's a kinetic energy term, remember I told you? Because it hops particles. You can also have interaction terms in second quantization. These have 4 indices generally, 2-body terms. And just note I'm writing these Hamiltonians in an order that all the daggers are on the left and all of the annihilation operators are on the right. And this is called normal ordering. And the reason I'm doing that is the same reason that I developed all these coherent states. It's because when I put these in the path integral, remember when I had h was just p squared plus x squared? So you operate forward with the x part and operate backward with the p part on that to get those matrix elements. And because it's Hermitian, you can do that. So it's the same in this case. If I have a coherent state, I can operate forward and backward without having to commute anything. So this is just called normal ordering. And I can construct a path integral for, the real-time time evolution operator, the unitary operator. But what's probably more useful is keeping in mind the partition function. Because if we're doing calculations, especially if we're doing equilibrium stat mech type calculations, what we really want is the partition function. And the partition function isn't just the partition function, it also gives us expectation values, like thermal expectation values. So and let's say products of operators, raising and lowering operators. I'll motivate the form of this expectation value maybe next class. I'll talk a little bit about Green's functions and so on. But let's just, for now, imagine that I want to calculate the expectation value of this thing. And, what is this notation? I guess we've maybe run into it before, but this is just, an average, if you want to call it that, over some grand canonical ensemble, right? So you have to work in some ensemble. It's grand canonical if we're working in the number, like in the Fock space. So some grand canonical distribution has different particle numbers. So just generally, we'll construct these expectation values by knowing a partition function. So let's do the path integral for the partition function. So quite generally, I could have Hamiltonian operators like this. If I'm grand canonical, keep in mind that there's a potential energy there, or chemical potential, sorry. That chemical potential occurs, in the ensemble or in the partition function as the value mu, which is the value of the chemical potential times the number operator, I guess, if you're working in occupation number, the occupation number basis. So this trace is just a sum over diagonal matrix elements. I don't know. Where this runs over the complete set of states in Fock space. So let's use what we know about the coherent states to just write the path integral, the many-body path integral for the partition function. And you can start with this expression. So this could be the motivation. This is what you want to calculate. You want to calculate some expectation value. We'll look at a few of these, or we'll look at the form of these. And this is sort of the ensemble I'm in. And this is this is how I understand that ensemble in terms of this occupation number basis, where I'm changing the number of particles based on creation and annihilation operators that occur in second quantized Hamiltonians, right? That's kind of the starting point. That's the setup. And now we have a partition function, and I want to get rid of the operators. I want to get rid of the second quantized operators that are occurring in here, and I want to do it by constructing a coherent state path integral. So you have enough information to do it. You can probably do it better than me. But I still have half an hour, so let's do it. So how would you start? Start from this. Resolution of the identity, it's like the only option you have, besides adding 0 to it. So we need this completeness relation, which I've just written over there. And let me write it like this. Sorry, I crammed it in here. I've just inserted a resolution of the identity. It's here, here, here. Did I forget anything? I think it's okay. There's an important subtlety here if we're dealing with fermions. So we want to get rid of all that sum over. We want to use the resolution of the identity over. Over Fock space, if you will, to get rid of this piece, right? You have to commute through basically these scalars, these operators. So this is a subtlety, but you'll look at it on your assignment. So we want to use this, but what we need to do is look at commutation of, say, these two inner products. So let me write like this. Couple scalars, basically, right? You never worry about this. You commute those two scalars through each other. You don't lose any sleep. Then you have the resolution of the identity, because you got that sum there, and you're done. But for fermions, when that field is fermionic, it's not so straightforward. You have to keep track of your minus signs. And what you'll get is this. So you can pick up a really important minus sign when you just commute these types of, Grassmann numbers through each other. So that's kind of fun. It's not that hard. Wait, I think it's on your homework. So in order to do it, just remember the properties of the coherent state and write this thing in terms of what it is. It's just. So I'll have you prove this minus sum I. Oh, that's too small, but it's a hint. So convince yourself of that fact that when you commute those two scalars, if you want to call them that, when these are Grassmann numbers, that you pick up a minus sign. And that minus sign, you have to drag that minus sign around through the entire d+1 dimensional path integral. And you already know the structure of the path integral, because what's going to happen now is you have, you have psi and psi here. So you have the bra and the ket. And then you insert a bunch of resolutions of the identity. But then at the end point of your d+1 dimensional expansion, you're going to flip the sign of the fields when you calculate the matrix element. Right at that, right at that one time slice, if you want, that I've always said is periodic, right? Or last time I said it's periodic for the partition function, it's anti-periodic for the fermionic case. And this is where it comes from. So it comes all the way back from basically the definition of coherent states. So when you're old and you're trying to remember where Matsubara frequencies come from for fermions, it's from that thing. I know it happens to me. What are we doing? So, okay. I'm going to write out this partition function. Let's just do it. Okay, so let me do it like this. I'll write it like that. Okay, that's cool. So you'll get something like this in the end. That row is that -1. So it's +1 for bosons and -1 for fermions. And then you have your nice resolution of the identity here. Right? So the thing you're going to start with is basically an expression for your partition function like that. So once you have that, you just construct it path integral in the usual way. You start inserting resolutions of the identity in between exponential operators that have been written as a product. Because if you introduce some small, infinitesimal time slice, okay, so I don't want to drag around that chemical potential anymore. I was just trying to remind you that it's there. So let me define H tilde as the operator. Okay. Just remember for grand canonical ensembles, the Hamiltonian has a chemical potential that's out. Or, the partition function has a chemical potential that's outside of the way we usually write the Hamiltonians. It's part of the ensemble. So I'll just put that in the Hamiltonian. Yeah, I think that's it. And then I just need, you're doing something like breaking up. Right, so you have a trace eta minus beta h. And you're going to break up that exponential, into either, I think it's delta taus, I called them before. So what you're doing is inserting resolutions to the identity. So trace. Okay, well, this isn't very. So inside here, you're inserting 1. I'm just going to write some next steps. So just remember what we're doing. So just like before, I have to have a notation that's like a product of a bunch of sums, if you will, that come from the resolutions of the identity. And this is what turns into my functional integral. So in this case, I can write it like this. So my time slice, which I'm calling tau, or my imaginary time slice, is, right, so I have a whole bunch of resolutions of identity inserted at all these different time slices. So I have that product over taus. I'll have an exponential. That comes from the over completeness for all these different taus. So let me label my states with tau. So I'll write down the important parts here. So I'm now expanded in d+1 dimensions. And in that expansion dimension, that imaginary time dimension, I start at tau equals 0. I go to tau equals beta, right? So it's inversely proportional to the temperature. So the lower your temperature, the bigger that dimension gets, that extra dimension. And you should be able to break this up into a product of matrix elements, H tilde. Oh my God. Okay. So we call this one delta tau. These all come from the resolution of the identity. H tilde, psi 0. Yeah, right. So the thing I want to emphasize here is that this thing here is what I've written over there with that rho. Okay, so number 1, it's plus for bosons, minus for fermions. But when you've written the trace, essentially this state has to be equal to this state up to that minus sign, which is now labeled by the imaginary time variable tau. So it means that this thing is just rho tau, rho psi naught. That's what you're talking about. And then your task is to evaluate these matrix elements, right? So you exponentiate that. And I guess I'll write it. Actually, that's where normal ordering is important. So we're going to get rid of all those operators. Okay, so I'm just doing this path integral in like 2 steps. So if anything looks confusing, go back and fill in all the details. But basically all the hard work was done by defining the coherent states, these psi's. And I assume I have a Hamiltonian written in terms of these second quantized operators. So then all of these matrix elements can just be evaluated. You just do it in first order, assuming delta tau is infinitesimal, and re-exponentiate. Oh yeah, so H tilde is no longer an operator. It's a function of the fields. Right? And since it's Hermitian, the normal ordering is used to diagonalize everything, basically. Because you can operate, backwards and then forwards like that. So anyways, then I have an overlap. What's that overlap? Yeah, remember it's not 1 for the coherent state. It's e to the psi psi. Psi bar psi. Okay, so you get that additional thing from the overlap, basically. And this is the step where you're normal ordering, and this is the step that you basically developed all the technology for. That's it. So just so we have some notation here. Now I'm going to have a functional integral fit this all. I'm starting to write small. Okay, so I have a functional integral. I have sums over tau, sums over the fields. I'll put these notes online if this isn't clear. Right, I have products of tau that come from the overlap. That's right. And then I have the Hamiltonian, or the matrix element of e to the minus tau times the Hamiltonian evaluated at, so psi bar is at time tau, like usual, but psi is at time tau minus delta tau. And I've lost track of this thing, so I'll just write it in this integral. So the boundary condition that psi at beta is rho times psi at naught. So just write that under the integral. I think that's everything. I don't think I dropped anything. Yeah, and the functional integral is just the usual thing. It's really just a notation, you know. A lot of the manipulations or the things we do with functional integrals, I mean, they make sense, but maybe they're not sort of completely obvious. There's a whole field of mathematics that works on functional integrals. So we're just using all of their stuff. So in this case, we have that product over tau. Then we have that integral of this thing, which is more complicated than it looks, right? Because it has d psi complex or d psi conjugate, d psi over pi to the, it's like 1 minus or 1 plus rho over 2 or something like that. So this thing's already a bunch, this is already jargon, right? We have this jargon here, then we have a product of those things, and then we're taking the integral limit and keeping track of the boundary conditions. And writing it as a functional integral. And remember that functional integral is like the price you pay for not having operators. Because everything's written either in terms of C numbers now or in terms of Grassmann numbers. And let me just combine things into an exponential again. Functional integral. I got to keep track of this minus sign. Let me write it like that, I think. So I have a field. I have too many brackets. Nah, maybe not enough. I don't know. 1, 2. So I have this stupid thing here. You know, I have to subtract 2 fields. That's basically how you get the time derivative out and everything, remember? And then the exponent. Okay, hopefully I'm not dropping things because I'm doing this quick, but look for these. I'll put these notes online. This is either in Nagaosa or maybe Niegel and Orland. Everything's in this textbook, Niegel and Orland, if you need like a reference. It just may be a little bit more opaque. Why am I writing this all out? I just want to show you the basic form of this thing in terms of what we're going to call the action. So just like in the Feynman path, just like in the single particle path integral case, take delta tau to 0. Do I have sums over tau? Yeah, I have sums. So every time you have a sum over tau, so all these discrete resolutions of the identity. And then this thing here, we're going to write as, so psi I, which we did in the single particle case, remember? Defines psi bar, I forgot the tau. Right, and the time derivative of psi I tau. So that last step, so when you see your path integrals basically written like this, remember it's come from this discrete difference. Okay? So then the final form of the coherent state path integral written in terms of this functional derivative. Just write that tau derivative like this, just make things look nice. That's tilde, just in terms of psi bar psi. That's it. And that's all in an exponential. So at some stage, it just looks nice because we've introduced this sort of symbolic jargon. But really, that's all it is, okay? It's the direct analogy to the single particle path integral with some subtleties. But it's subtleties that if if we look at the coherent states carefully, you'll see exactly what they are. So one is this thing here, of course. And then also the idea that you might have Grassmann variables. And you can make this even more compact by writing this exponential. Is just e to the minus s. To remind you of an action.
Is the first term also interpret as the Berry phase, or with these?
Yep, that's the Berry phase, yeah. So it's the same thing, right? It was like, what was it before? It was p times x dot, right? So now it's like you have the field and its conjugate, right? And this is the time derivative of the field times its conjugate. Yeah, so exactly. So it's the same thing. If you can get rid of that Berry phase, like there's one more step. This is a Hamiltonian form, which is the most fundamental form of the path integral. If you can get rid of this through some integration, which occurs when you have essentially non-interacting Hamiltonians, so A dagger A, then everything's Gaussian. You get rid of this thing, you get rid of the Berry phase, and then it's essentially entirely classical. So let me just mention the significance of these boundary conditions. And then next time we'll talk about a little bit about correlation functions. And if you're used to calculating correlation functions, or if you're doing scattering experiments or transport experiments, then you're used to seeing, maybe you're used to taking data in frequency space, but oftentimes your calculations are in imaginary time, and you have to transfer between time and frequency and so on. And that's where the Matsubara frequencies come out, and that's where this boundary condition matters here. So let me just look at this boundary condition real quick. So in this path integral, the operators are gone. You essentially have fields, a field and its conjugate, if you will, which live in this d+1 dimensional space in Euclidean time. And it's those fields which have this boundary condition. So it's imaginary time here, I guess. You ever see John Oliver interview Hawking? And Hawking's like, what's the one thing you want people to understand? And he said imaginary time. And then John Oliver's like, oh, it's just a wick rotation of like, it's just so dumb. Yeah, you should watch it. I'm sure you had to practice, So what am I talking about? Oh yeah, so the fields are periodic or anti-periodic. So periodic, anti-periodic on the interval. Tau goes from 0 to beta for bosons, and anti-periodic for fermions. So because of this periodicity, you can decompose the fields into their Fourier components. Just like almost a Fourier theorem thing. So it just exists. So, and this gives rise to the frequencies associated with this Fourier decomposition. So psi of tau. So I'll just use some standard normalization. So just think of that as, this is just a length. Beta is just your length in imaginary time. So I'll define the Fourier transformation with the frequencies omega. So the field and its conjugate. Just define a conjugate field in Fourier space. So that could be a different symbol, right? That's like the, that's the field labeled by the frequency that's occurring in that sum. But I'll just call them psi of n's. Then the periodicity condition. So bosons, let me do them first. Periodicity condition is periodic, periodic. So that means that your field at some time tau, it's the field at tau plus the length in imaginary time, right? So tau plus beta. Yes, I'm going to go with that. And so yeah, so all you do is you just insert that condition into the Fourier decomposition. Right, so your exponential just splits into two, and then e to the minus omega n beta. I feel like I missed something. An I. Right, so in order for that thing to equal that thing, then this thing has to be 1. Okay, right? So omega n is just, so it's got to be 2n pi over beta. So this sum should be over, it's either over Matsubar frequencies or n. So for fermions, you're anti-periodic. All right, so psi of tau. If you cross beta, your field picks up that minus sign. So then the same thing. So then your e to the minus I omega n beta has to equal minus 1. So that implies your frequencies, right? They can't be, they're not 2, so it's 2n plus 1 pi over beta. So those two things are your Matsubara frequencies. So if you do quantum Monte Carlo, you solve this Berry's phase, you put this thing on a computer. You can get correlation functions, which I haven't talked about too much, but you get correlation functions in imaginary time. And then to relate these things to, say, like a spectral function or to neutron scattering experiments or something like that, you typically want stuff in frequency space. So then you have to analytically continue from the imaginary time axis into these Matsubara frequencies, which isn't always sort of a well-defined procedure. And that's one of the difficulties of doing purely classical, I guess, calculations in imaginary time. So we'll talk a bit more about correlation functions and Green's functions and Matsubara frequencies next class. The pole structure of the Green function is related to the spectrum somehow, so that's important. But I think we won't spend too much time on that, even though that's somehow the point of the class. But I want to move on to the spin coherent state, because the spin coherent state's fun because we can fool around with the Berry's phase a bit more. Okay. So I'm driving up to Huntsville right now, so there's no class on Thursday. But luckily, I remembered to get a new assignment for you guys. So homework 2 due in 2 weeks. You guys at Mac, if you're doing the homeworks, scan an email, and you guys bring me your homeworks. Or put them under my office door or something like that. Okay, so I'll see you guys in a week.